Okay, another example along the lines of what we were doing in the last segment. An object has a mass of 63.5 kilograms. What is its weight on Earth? And on the moon? Gravity on the moon is 1.62 meters per second squared. Okay, so what we're given, mass is 63.5 kilograms. Gravity on Earth is 9.81 meters per second squared. And gravity on the moon is 1.62 meters per second squared. We weren't actually given the gravity on the Earth, but you know that number is a constant, so we'll get so used to that after a while that it'll be second nature. So what we have to do is find the weight on the Earth and the weight on the moon. Weight on the Earth is going to be mass times the gravity on Earth, and that's going to be 63.5 kilograms times 9.81 meters per second squared. And that's going to be, let's see, to the proper number of significant figures, that's going to be 622 newtons. The weight on the moon is going to be mass times gravity on the moon, and that's going to be 63.5 kilograms times 1.62 meters per second squared. And that will be 103, rounded off to 3 significant figures, newtons. So, I've been saying that gravity on the moon is about 1/6 what it is on Earth. And so, as you can see, your weight, or the object's weight, would be about 1/6 on the moon what it is on Earth. Okay, and if you wanted to know what is the weight in pounds, you would need a conversion factor. We have a conversion factor here on Earth between pounds and kilograms, which is basically 1 kilogram is about 2.2 pounds, or let's see, 1 pound is 0.454 kilograms. But that only works on Earth because that assumes that gravity is 9.81 meters per second squared. So that conversion actually would not work on the moon. There is a conversion also between newtons and pounds, and that's actually better to use because newtons and pounds are both units of force and no assumptions are made about the value of gravity. So 1 newton is equal to 0.2248 pounds. So there's your conversion factor. And the advantage to this is that it works anywhere, not just on Earth. So if the weight on Earth is 622 newtons, 622 newtons times 0.2248 pounds for every 1 newton. Notice newtons cancel, we get pounds as the unit, and we get, let's see, 139.8256. That rounds off to 140 pounds. And the weight on the moon is 103 newtons So 103 newtons times 0.2248 pounds for every 1 newton. Again, newtons cancel, and we get 23.1544, which would round off to 23.2 pounds. So that would be the weight on the moon in pounds. Okay, so if we recall, net force, to determine when a force causes an acceleration and when it doesn't, we need to define a net force. Actually, we haven't discussed this in great detail. I mentioned it kind of in passing. So what we need to determine to find out whether a force causes an acceleration or not is the net force on an object. Or in other words, the total overall force. The net force acting on an object is the total force determined by all of the forces acting on the object, taking into account their direction. So you need to count both magnitude and direction for all of these forces in order to figure out the net force. Because two forces that are working directly opposite each other are going to cancel each other out, at least partially, if not entirely. And so you have to take that into account when you're trying to figure out the net force on an object. So if all of the forces are acting in the same direction, we just add them up. If some of the forces are acting in opposite directions, we subtract them. All right, so as an example, if you have a box sitting on a floor and you have a force acting toward the left with a magnitude of 12 newtons. And so we can think of that as not only being a 12 Newton force, but 12 newtons to the left. And we have another force with a magnitude of 15 newtons, also to the left. The net force would be 12 plus 15 equals 27 newtons left. Or if we were using mathematical signs, that would usually, well, the way we normally do things, that would be considered to be -12 plus -15, which would equal -27, because things that go to the left are usually considered negative. So another example, if we have a box sitting on a floor and we've got one force acting to the left at 15 newtons and another force acting toward the right at 6 newtons, the net force would be plus 6 newtons, or 6 newtons to the right, plus -15 newtons, or 15 newtons to the left, which would be -9 newtons, or 9 newtons to the left. That would be the net force, because these forces are acting against each other. It's certainly possible that you would have forces acting at an angle to each other. Say 10 newtons to the right and 12 newtons kind of at an angle up, sort of upward and to the right. And that gets complicated. That calls for the use of things like sine and cosine in order to figure out what proportion of this force is going to the right versus what proportion is going up. And so that's a little beyond what we need to get into in this class. So we'll just say that that's complicated and we don't really have to worry about it. Another example might be a box that's sitting on the floor and it has a downward force due to its weight of 4 newtons. At the same time, it has an upward force, which is known as the normal force, exerted by the floor on the box of plus 4 newtons. And the net force in this case equals plus 4.0 newtons plus negative 4.0 newtons, which is 0 newtons. So the box is at rest. In other words, it's not moving. Although more accurately, it would be more accurate to say there's no acceleration. In fact, I'm not even going to say that it's at rest. And no force, no net force means no acceleration. It doesn't mean no movement. Actually, the box could be moving, but it's not accelerating. It's not necessarily moving because being at rest also means no acceleration, but it could be moving at a constant speed. That would be another possibility. Okay, there's another possibility that friction might be involved here. If you got a box sitting on a floor and you apply 8 newtons for force toward the left, so in other words, negative 8 newtons, but friction is applying 8 newtons in the opposite direction, then it doesn't move. Friction is a force that opposes applied force. And friction often results in a net force of 0. In that case, if the net force is 0, the box wouldn't accelerate, but it could move at a constant velocity. That constant speed could be 0, which would mean the box actually isn't moving, but it would be a constant speed either way. Okay, so objects that are moving at a constant speed in a constant direction are objects that have a constant velocity. And when the net force on an object is 0, the object could be either, well, if the net force is 0, that means the acceleration is 0, and the object could be at rest, which just means that the constant speed is 0, or moving with a constant velocity. Moving with a constant velocity greater than 0. Okay, so this case, when net force is 0, that's known as balanced forces. If the net force is not 0, that's also known as unbalanced forces. And the object must be accelerating. Remember what we mean by accelerating. That could be speeding up or slowing down or changing direction. Or some combination of those things. Okay. If a particle is moving at a constant speed as it moves around a circular path, So if it's going around a circular path at constant speed, the forces are unbalanced. We know that that must be the case because the object is changing direction, and that's an acceleration. Okay, so remember, even if your speed isn't changing, if you're changing directions, you're accelerating. And that means the forces are unbalanced. So an object in free fall is subjected to unbalanced forces because it's accelerating. So if an object is in free fall, it's accelerating, so that means the forces must be unbalanced. Once the object hits the ground, it's no longer moving, and at that point, the forces are balanced. Okay, so when, say, a skydiver jumps out of an airplane, the skydiver will be accelerating towards the Earth, and that means that the forces on the skydiver are unbalanced. Once the skydiver opens his parachute, the acceleration will slow down. The acceleration is reduced, in other words, but velocity is still increasing. It's just at a much slower rate. So as long as there's acceleration, even if it's slower than it was before, the forces are still unbalanced. It's just that the forces maybe are not as unbalanced as they were before. Eventually, though, if the distance the skydiver is falling is great enough, the skydiver could reach terminal velocity, which means that the air resistance pushing up on the skydiver is equal to the force of gravity pulling down on the skydiver, and the velocity will no longer be increasing. In other words, acceleration will be zero at that point. That is, the skydiver will be falling at a constant velocity. And that's terminal velocity. And since the skydiver is not accelerating anymore, that means at that point the forces are balanced. So if there's no acceleration, the forces are balanced. If there is acceleration, the forces are unbalanced, and vice versa. Interestingly, the terminal velocity for a person falling toward the Earth is something like 120 miles an hour, which seems pretty fast, but keep in mind that if we didn't have resistance from the air, that is, if you were falling toward some heavenly body with acceleration similar to Earth, with gravity, similar to Earth's, but no atmosphere, there would be no limit on how fast you could fall. You could keep going into hundreds of miles per hour before you actually hit the surface. And so you can always console yourself if you're going skydiving and your parachute doesn't open. You can at least console yourself that you won't fall any faster than about 120 miles per hour before you hit the Earth. I'm sure that's great consolation. Okay, the next topic is Newton's laws of motion. Actually, we've already seen one of them. F equals ma, or force equals mass times acceleration, is one of Newton's laws. And we'll get to that along with the other laws. Although we're close enough to the end of the 30 minutes for this segment that I think I'm going to call it there. That'll be the end for this lecture. We'll pick up Newton's laws in the next one. So I'll see you then. Bye-bye.